Hi, I'm Ryan Tiemann. I'm the team lead for the LEMA team. We're working on this project in conjunction with Flanders Electric, who Mr. Stokes is a part of there. We go back in the bright red shirt. He's there, as well as Mr. Gunnell. He's here somewhere, I think. So we're working on this project with Flanders Electric. Just a little outline of what our presentation is going to be. We're going to give introductions and talk about what our goals and deliverables are, the scope and specification of our project, and then delve into what we actually built and designed and prototyped and what we've got accomplished here today. So our introductions. Wait for it. Here we are. Flanders Electric. I want to talk a little bit about our sponsor. They're a national company that builds electric motors and drive control systems for electric motors. They also have a division that does technical motor testing. So they go out, send technicians out to all areas around the country and do testing on motors to see how what is the health of those motors. Mr. Gunnell spent all spring in South Carolina, I believe it was, running through paper mills, testing all their motors while they have a shutdown. And it's this type of process can be very costly and time consuming for the client. They're having to pay technicians and they're having to pay for this service that they're having to do, and it also takes time because they have to shut down the plant while they're doing it. So that's a little bit about our company that we're working with. This is our team. Like I said, I'm Ryan Tiemann. This is Billy De Constanza. He's in charge of case design as well as in circuitry. Logan Bryant here was in charge of the circuitry design, and Abdul Aziz did a lot of the PCB manufacturing and design, and then Logan Turner was our programmer. We also had 6 junior members that were part of our team. Some of them are here today, so we really appreciate their help. The goals and deliverables of our project. We wanted to do some testing for an induced voltage when we connect up to motors, because we don't know if the circuit could be on, human error happens, or the actual motor could be moving, in which case it would be acting like a generator. We also want to accurately run the tests and measure the resistance and the inductance of each phase. And output the diagnostics, which is previous units that Flanders uses, does not give a diagnostic output of the motor. It just says, here are the values, and the technician has to determine what's going on in those motors. So what we're trying to do is take Flanders brains and their test units and put them both into one unit. Also, we want this to be user-friendly, in that this is a product that Flanders wants to sell to companies so that they can do their own testing. So it doesn't need to have a lot of training of how to hook up, how to operate properly. It needs to be able to just give to a technician, and in 10 minutes of training, show them how to hook it up and how to run a test, it'll be good to go. So our high-level deliverables, we wanted to bring a final prototype that Flanders can use, and then also we've got reports and presentations, including this. This is a industry product, and that all the stuff is going to be turned over to Flanders here at the end of this semester for them to continue on with it. So now I'm going to talk about our scope and specifications. This is the PDMA unit, which is predictive motor analyzer. This is the unit that Flanders currently uses, and as you can see, it's basically a decent-sized briefcase. It coils a lead acid battery that powers it, and it has to have a laptop to control it, run the test, and then output all the results. It's very expensive comparatively. It also is very heavy. It takes a lot of technical knowledge to run it and to be able to interpret the results. This is more like what our unit is going to be. This is about less than 120 cubic inches, so it's going to be a handheld device. I've got our case design up here on the table. If somebody wants to take a look at it. Weigh a couple pounds. We also designed it so that it would run at least 30 tests, which is the approximate amount of tests that or the maximum amount of tests that a technician could run in one day. so that way they're not having to change out batteries every so often. We want to include basic skill level required and have low cost so that companies can afford to buy 1 or 2 or 3 of these and put them in their plants and have their technicians do some testing. So now I'm going to turn it over to Billy, who's going to talk about our circuitries.
My name is Billy DeCostanza. First off, I just want to go ahead and let you know what we're going to be testing for. The first test that we go through is going to be the induced voltage test. We can leave that test and go into the lead test, and I'll get into that in just a second. And we also go and do the resistance and balance test. That way we can find out if the motor is going to be good or bad based off the resistance and balance. And then from there we're going to go do the inductance and balance test, which will let us know whether or not the motor is good on that. The first test that we're going to do is the induced voltage test. If the motor is hooked up to a fan or a pump and we have fluid running through there, the motor is going to be rotating, ends up turning into a generator, and we'll have voltage on the lines. We can't test with the voltage on the lines. And so what we're going to do is we're going to say, hey, there's voltage on the lines if it's continuously turning, or if there's a induced voltage that's just been left on the motor, we can drain that. And so we have that set up, and it's been working very well for us. And we leave that test, we go into the lead test. Here are the leads right here. These 3 leads here, and we want to make sure that we have a good connection. If we don't have a good connection, we're going to get bad results. So we want to make sure that the lugs aren't corroded and that sort of thing, and so we go through and make sure that that's good on that side, and then we can move on from there. After that test, we're going to go into the impedance testing, and I'm going to let Logan talk about that.
Okay, to find the impedance of the motor, we have 2 different tests. We have a DC test, which will apply DC voltage to the motor, and from that we'll calculate the actual resistance of the copper inside of the windings. And then we have an AC test, and we'll use that to calculate the inductance of a set of windings. And then we'll compare the different sets inside of the motor to each other to come up with an imbalance measurement for that motor. Okay, our unit will work for any 3-phase AC motor, regardless of whether it's delta or Y configuration. Here's just a simple schematic, and we have all these relays to switch between different sets of coils in the motor and the induced voltage test. We also have to show where we're measuring our voltages to calculate the current and voltage that's being applied to the motor. Okay. Now I'm going to pass it up to Abdul to talk about our PCB design.
For the PCB design, we have 2 phases. The first phase talk about the schematics. We use for the schematics PCB artist software because it's friendly and we can see the traces with the color, and you can tell which this trace and everything is very clear in that one. But we can't create your profile by PCB artist for the PCB. That's why we choose for the PCB design. We start with the multi-sim, and after that we found out the maximum layers we can get from that software, 2 layers, and we need 4. That's why we moved to KCAD software. We can get up to 16 layers. As we see here, this is the PCB, the final PCB. This is the current ADC, and this is the voltage ADC. This is the main components and the microcontroller. This is the first prototype we have, is hardwired. As we see here, you can't tell anything's here, just the one he created, he can't tell. Yeah. After 300 hours, more than that, we get this PCB. It's all the components fit in one board, like 4 inches by 6 inches. Now we will pass the time for the program.
The brains of our device is a microcontroller made by Texas Instruments. It's the T-C. It's actually one of their more powerful ones. And you can see the chip itself here. It has a couple of built-in modules that are really useful to us. One of them is an analog to digital conversion module that we use for reading our analog signals. And another one is the display driver. So we can plug a display basically right into pins on the microcontroller, and it works seamlessly. This development kit is what we used in our initial prototype, where we would jump over to other protoboards. But on our final PCB, we used just the chip itself, which you can see here. Programming was done in Texas Instruments' own development environment, Code Composer Studio. Thankfully, Texas Instruments provides some very good drivers and routines that we're able to make use of, so that we don't have to deal directly with the registers in the microcontroller. Using their drivers and configuration tools, we were able to write our own custom routines and configuration for doing the tests we needed to do, and we were able to abstract the code. Even though it's in C, we were still able to make it pretty well organized in order to rearrange the steps of the test. Here you can see how we're programming our custom PCB using circuitry from the development kit. They included built-in debugger circuitry. That's how we program our PCB. Our device outputs basically 4 results. The motor will pass, or it will pass with a warning, or it'll fail based on one of the 2 tests that we run. Either the inductance imbalance is too great, or the resistance imbalance is too great. And these are the thresholds that we've been indicated from Flanders that should determine whether it's a failing motor or not. And so one of these 4 outputs is displayed on our nice color display, easy to read and understand. If it's a failing result, it'll display the values of how much it failed. And with that, I'll hand it over to talk about results.
Okay, so these are some of our test results with comparing our PCB to the PDMA. This is the resistance imbalance of a bad motor, and you can tell it's a bad motor by how much variation and resistance there is between the 3 phases. And as you can see, the PDMA says it's 16.6% imbalance, and our unit says it's 15% imbalance. And this is the inductance of a bad motor. You can tell it's a bad motor by how much imbalance there is between the coils. And this is a resistance imbalance of a good motor. While our imbalance is slightly high, it is still significantly different from a bad motor. So we are able to tell the difference between the good motor and a bad motor. And this is pretty much the same thing except for the inductance inside of the good motor. Now I'll pass it off to
So I just want to, in review of all of our goals and project outline, I just want to talk about what we actually accomplished and what we're able to get done on this. As I said before, this is a research that we're doing for Flanders Electric, so we're trying to provide them with the best possible prototype that they can work with, and get the major R&D down for them so they can try to modify this and put it into production. So we wanted to obviously test for our induced voltage, measure our resistance, inductance values, and output the diagnosis based on those values. We also wanted it to be user-friendly. Again, we wanted to provide a prototype that we could do some field testing and also presentations, etc. So where we're at, we completely redesigned the testing unit. Last year's team did an initial proof of concept with this project, and so we try to take some of their ideas and their designs and take it to the next level. We've included all the testing steps that we needed to do, the induced voltage, make sure that we're connected properly with a leads test, resistance and inductance testing, and also provide diagnostic output. And as well as top of that, we designed a PCB and prototyped it. We've had 2 iterations of the PCB, and we made it user-friendly. This is literally a picture of our final product. So it would have one button, which is just test button, and then just an on-off switch for battery saving power. So we've done some case design on it as well, just to try to see what kind of package we wanted to put it in for the end user. So now we want to try to run a demonstration here for you guys. We've got it set up over here, and we're going to try to broadcast it.
So we were testing this this morning, and we were running into some issues with it freezing up at the resistance imbalance test. So we'll see if that happens this time.
Okay, so the device will start by testing for an induced voltage on the coils to make sure there's nothing there that would damage it when it does the impedance test and the leads test. So now it should be applying a DC voltage to the coils to calculate the resistance.
Yeah, the phenomenon at play here is just Ohm's law. We're applying a voltage across the coil, measuring the current through it, and dividing that to get the resistance. Now, since this is an inductor, essentially, the coil is a motor, it takes a little while for the voltage and the current to settle out. And so there's a process that's watching that. Doesn't normally take this long. So after it finishes the resistance imbalance test, it moves on to the inductance imbalance test, in which it applies an AC voltage across the coil and actually watches the peaks of the resulting signals and looks at the phase difference between the current and voltage peaks in order to calculate inductance on each of the coils. And when it's done that, it would display the output. It looks like it's frozen up on us. So we would love to show you the output sometime. So it's easy. I'll hand it off back to Ryan again.
So let's And just going over what our schedule was for this past 2 semesters, we had some delays at the end of the last semester, in that it took us longer to get our prototype working and our hardwired prototype. And then also we had some issues in our second phase after we started ordering the PCBs, so it caused for some delays in us getting our actual boards to work with. Some of those were out of our hands, but we're glad to be able to have something that works now for them. So, and our budget proposal, most of the costs went into prototyping the boards for doing single or just a couple units of PCB prototyping and assembly can be very expensive. So that's just what our final budget ended up being. And I'll open it up for questions now. Yes, sir.
Okay, a couple of questions. First one's kind of trivial. Is there a story behind the word Woody on one of the plugs there?
Right. We had two boards, and we had to somehow distinguish between the two because they look exactly the same.
Okay.
So we had, when we made the last PCB set, we had two of them made and assembled and sent to us. So we just had to name them after some famous duo. So one was Woody and one was Buzz.
Okay. And the less frivolous question, I guess, is for your inductance test, what frequency do you excite the windings with? 60 hertz, 180 hertz, what?
60 hertz, yes.
Okay.
Yep. So then we're using the peak measurements on the current and the voltage. That's why we have two different ADCs that are measuring each one of those, and then we compare the phase shift between them to calculate the inductance. Yes, sir.
Probably about 3 different questions since you have multiple disciplines here. Was there any thought of using a coupled connection or anything that would get rid of lead variances of connecting to the motor?
We were looking into some. We would have some. There is some. We've experienced some variation in between tests where they would the actual numbers would vary a little bit. Some of that is due to the differing internal resistances of the relays. We did not pursue that specific type of connection that you're talking about.
And the second part of that would be what were the accuracy of the measurements and how were they verified? I noticed that they differ in different directions than your reference device test system.
Yes. This PCB that we've gotten, we got it just a couple weeks ago, and so obviously there needs to be some calibration that we have to continue doing in it to get it more accurate. We were able to get it a lot closer with our hardwired prototype just because we had a lot of time to work with it and see how it works and adjust slight little things in the code. And but yeah, the accuracy is basically we have to take and measure how accurate the components individually themselves are measuring, and then we can graph how their error and how they change compared to what the actual values are, and then make up the difference for that calibration.
And the last part of that question was from a software perspective. I noticed when you started there, there's very little feedback in terms of test operation. Normally when I design something from a software perspective, I like to say that I'm doing something, that I'm making progress, so somebody doesn't throw it a wall, thinking that, hey, it's not, it's broken or something, they just be waiting. But part of that software would also normally deal with unit calibration, going back and testing a known sample in between runs and possibly compensating for temperature.
That's correct. In fact, we have 2 modes of operation, and one of them is a more advanced user mode that shows all the data that it's collecting as it's running. And so we don't intend typical technicians to use that mode because the idea is that they just see the results, they see that it's testing, and so we intentionally limited the user feedback in the normal mode. But we do have that exactly for what you said, for the purposes of going back and checking that it's reading correct values.
Any other questions?
It's probably kind of a dumb one, but I take it some of these motors can be sick and still run.
Yes.
And so otherwise I'd say you wouldn't need your little tester to tell you the thing wouldn't turn. But
Yes. I have some background in industry, and so I was an electrician for 9 years, so I've got some experience around motors. And yes, some of them will run for years and years and years, and you'll walk up to them, and yeah, they've been running, but they're 200 degrees, and that means that something's not right, even though they're not they're not worn out enough to trip the circuit breaker, they're physically worn out.
And that they are in peril
Yes.
of failure at an inopportune
Yes.
time.
And
We'd
part-
like to
and part of the-
take them down in a controlled manner.
Exactly, and that's what we want to do, because if they do go down, sometimes it can be catastrophic and result in like arc flashes, and we don't want, this is a device that we want to try to do some preventative testing so that we can see, okay, this motor is going bad. Part of the thing that the PDMA unit does and what our unit can be adapted to in the future is storing motor, like logging data for motors, so that you can see the trend of how a motor is going. Yes. Yes, sir.
For industrial applications, has any thought been given to design of making it hazardous area rated?
We did talk about that at the beginning of the project, because obviously it'd be like in chemical plants or oil plants or even paper mills and stuff. You got dust fibers. We decided that was outside the scope of our project, but yes, that would probably have to be taken into consideration if we wanted to ensure that it was intrinsically safe and such like that. So,
Tell me about a decision you had to make based on cost.
Decision we made based on cost.
2 PC board blanks instead of 3.
Yes. Well, some of the times it was cheaper, or it was the same price to make 4 PCBs than it was to make 1. And so sometimes it's like, well, let's make some extra ones just because it's not really going to cost us anymore. And that way we can have several units that we can work with.
Can you go back to the previous slide because you have your budget up to?
Yes. Some of it also was time, because we wanted to work on, try to get product out to it, and so we had some difficulties dealing with the outside vendors who were building our PCB, getting things in a timely manner. So some of that was, some of the costs were driven up because we had to try to push them to expedite things. So that's also. Yes, sir.
I was wondering, when using this testing device, do you see if it had the same results as, say, the $50,000 machine?
Yeah, we were comparing it, like we showed on the graphs. Those are actual comparisons of the same motor between the PDMA unit and our unit. So, yeah, we were comparing it. We were trying to see how we can calibrate it to get it within the range of the PDMA. So.
Okay, I think that's good with time. Thank you very much.
Thank you very much.